Today's topic, LORA, the level of repair analysis in all its complexity. Well, let's first go over a brief agenda. We're going to talk just a little bit about Syscon and who we are. Many of you may be customers and users of OpaSuite already, but some of you may not be and want to know a little bit more. We're going to cover what a LORA is, all of the complexity, where it comes from, its application, and a lot more of the detail that I think needs to be unwound and looked at if we're to truly understand how a LORA is to be conducted and what tools to use for it. We're also going to talk about some LORA use cases. I'm going to bring up 3 particular use cases that we're going to go through, explain in detail, understand what those pitfalls are and how they should be handled, and then we're going to apply OpaSuite against it directly. So that is today's agenda. And so just a little bit about us. Again, some of you may know us, some of you may not. And for those of you who don't, Syscon is the provider of OpaSuite. This is a predictive analytics tool that seeks to optimize performance against cost. Now, it's been around for quite some time. It has lots and lots of capabilities. We're only going to be looking into a very small portion here this morning or this afternoon, depending on where you're at. And that's going to be the LORA, the level of repair analysis. So what is a LORA to start with? This is probably one of the most important things we're going to talk about here this morning. And to make sure that we're all on even ground, I'm going to be referencing where LORA really comes from. So I have excerpts here from DAU and from the 1390 Mill Handbook. So LORA, as you see there in the first bullet, is an analytical methodology to determine the level of repair of an item that will be replaced, repaired, and discarded based on cost considerations and operational readiness requirements. So right from the get-go, the LORA is extremely focused on both cost, but also performance. Now, depending on where you come from, right, whether that's the DoD or if it's the defense industry, that priority may be one or the other. Typically, we see that the DoD has their priority metric on performance, availability, and cost is more of a constraint. Whereas industry tends to have the cost as more of the priority metric. Either way, LORA is going to focus on both of these items, right? Now, you may not be totally familiar with a LORA in all of its detail. We're going to go through some of it here. So the Mill Handbook 1390 is a good place to start. It goes over everything. It's a bit of a dry read. But at the end of that, you're going to see this is a very complex thing. We like to think, or maybe some people have come to think, that a LORA is you just take some data, you put it into a tool, you hit go, and boom, there it is. It's an exceptionally complex analysis, right? Very, very complex. We're talking about hundreds or even thousands of parts and the different combinations that would make up if you are to replace something or repair something, and where does that replace and repair occur? Literally could be billions of different combinations in there. Now,
hey, Jerry,
it used to be,
hey,
yes.
Sorry to interrupt you. I think we're still on the About Syscon slide. I don't know if you've advanced it, and your video is getting a little bit choppy, so you may want to turn the video off.
Okay, thank you. Just a minute, folks. Let me go ahead and do that.
Okay, now we're seeing the what is a LORA slide.
Okay, excellent. All right, sorry about that. So again, there it is, the first bullet, right? What a LORA is, going over, and we're particularly looking at this cost and operational readiness requirements and its complexity. When I did a LORA, it was a bit of an analog way. This would have been 15 years ago now, something like that. You get a bunch of maintenance officers in room, a bunch of supply officers, some other folks. Everybody sits down with the operators. All right, so what is the best way that we're going to do this? We used things like Excel to augment what we were doing and the decisions we made. Of course, this was more of an in-service type of LORA, and we're going to talk about that for sure. But the decisions that we were making in there was very much influenced by those maintenance officers, those subject matter experts, the SMEs. And it's important to understand where SMEs fall into this because it is so complex and there's so much nuance to it. We give a course called Opus for Managers, and it is a lecture series, about a half a day, and it's designed to inform managerial personnel of how to properly employ a modeling capability within their business or their use case. And we go over a bevy of different things, but one of the items that we stick on is the importance of subject matter experts, because the data of any type of analytical calculation is really the foundation of the outputs. Yes, some data is more important than another. There's a very easy way to do a sensitivity analysis, especially in Opus Suite, that can tell you what swings the needle the most. Some data elements may be minorly affecting the outcome, where there are going to be some that are a primary effector of the outcome. And so when we're looking at validating those important data points, the SMEs really come into play. We could look inside of a technical manual, and the technical manual may say that takes 2 hours to replace. You talk to a maintenance officer, he might laugh at you, but yeah, try 2 days. There's a huge difference between those. They may know when you are going through the data and you see an order of 50 of something, the maintenance officer may be able to tell you, well, what happens when we get low stock, we order 50 off of a single repair order. One is applied to the system, the other 49 go into stock. I know that's substandard. I'm just coming up with an example. The point is that there is lots of different things that we need to consider coming from those SMEs, and we need to be able to account for those in the tool that we use. If a maintenance officer tells us that this unit over here is far more proficient in repairing things than that unit over there because that's the schoolhouse, or maybe that's an overseas location and they work a lot more hours, therefore they're able to crank through a lot more repairs in any given day than this unit over here. We need to understand that is the truth, and that needs to be part of the calculation of a LORA, because if not, the LORA is going to fall short. Of course, we've always heard the term garbage in, garbage out, but if you don't consider all the right items in the first place, then those are not going to be part of the equation, and therefore the answer is not going to consider those elements. And not considering a portion of the system that you are looking to do a LORA on, whether that is a fleet of F-35s, the fleet of JLTVs, or something like a system as in terms of a depot, right? A depot is also a system. So these complex things, they need the right tools to support it. And it's very important that in all this complexity that we're looking at here, right? So in that second bullet for complex engineering systems containing thousands of assemblies, sub-assemblies, components organized into different levels of indenture with different possible repair decisions, what does LORA seek to do? Optimize, right? Repair and maintenance facilities, right? Optimize what is the best repair decision, what's the best maintenance policy for this part here at this time. Within the realm, always considering there at the top that operational readiness. Very, very key that we remember that. It's not just about what is cheaper. It's about what is doing better for the entire system. And if we are to consider that it was better for the entire system or the enterprise or the fleet, we need to ensure that we are in fact looking at that whole enterprise. Okay, so there are two general applications of a LORA, right? Non-economic and economic. Non-economic deals with those things that lay outside the system itself. We're talking about, let's say we have a new unprecedented system coming into place that has some sort of technology that is non-existent right now. Well, non-economic LORA was going to look at, well, are there any technicians that could repair this at this time? How many technicians are we going to need to actually do something like that? Where should those technicians spawn from? Are those electricians or machinists or mechanics? So on and so forth. And these are all very important things to discuss and analyze. And a lot of those items can actually be put into Opus Suite as a consideration for the LORA itself. If we know that going to have so many mechanics and they have to be trained, and there's a training cost of getting those mechanics stood up to be able to effect a repair. Well, that should be a consideration inside of the second part, which is the economic LORA. Now, when we say economic LORA, this is going to be, shall we say, the standard definition. When anybody says, well, we're going to do a LORA, they're typically going to be referring to an economic LORA, where typically you will identify, I'm doing a non-economic LORA to make it distinct from a quote-unquote normal LORA. But when do you apply this, right? Well, it depends on where you're at in the life cycle. So we see here, again, this is out of the 1390. We see a little diagram here of the life cycle of a system. And the short answer is all the way from you see that the pre-material development all the way through sundown, right? From concept all the way through sundown is where a LORA is going to occur. The type of LORA, the focus of the LORA, the data used in the LORA, and the scope of the LORA are going to change throughout the life cycle. When we're talking about early days, right? So pre-milestone A up through, say, a little bit after milestone B, we're going to be looking at things like those larger items, facilities, number of technicians, what are those limits of MTBF that we can support within a repair facility. Like we could have a depot line that could handle X amount of engines at a time, per day or per month. Does the early look into the system look like we're going to break that or not? As we start moving down, we start getting towards where the thing actually exists. Then we're going to start performing the actual repair discard portion of it. We're going to be looking at those SMR codes, trying to develop those SMR codes. We're going to be taking the data that we're getting from prototyping in the IoT&E phase and using that to inform the LORA. Now, a LORA should be used throughout the entire life cycle of the system. It's not a one and done. It isn't, we do it there, pre-milestone C, set the SMR codes for provisioning, and boom, we're done. One of the reasons is going to be because the data that we're gaining from those early days, while extremely valuable, is not the final data. That system is going to change. It's going to mature through time. Now let's think about, the reason that a system fails in general is going to be by nature of how much it's used. And while this is good information to have in the IoT&E phase, it's not the end of the story, right? When we get that system into FRP and it goes and it hits the fleet and we have our service members using it like it's meant to be used in an operational setting, you're going to get a lot more operational hours. You're going to have a lot more systems. You're going to get a lot more of the averages. And so the data that represents what is happening is going to change. And you're going to have larger failure rates, or things are going to break in different ways, and so on and so forth. So it's going to develop over time. And those SMR codes, while developed at the very beginning, and obviously we have to have, deserve to be looked at again. Now, typically what happens is we do this when it becomes in service, right, as needed. If we're going to go over, it's like an ECP or something like that. But there should also be a planned use of a LORA, application of a LORA, about every 5 years or so, just to make sure that we're running at an optimal state, optimal as in the highest performance for the least amount of cost. So depending on where you're at within the life cycle is going to dictate how you're going to perform that LORA. Not only that, but also think about subsystems and components for any truck or tank or what have you. Like for instance, if we have a tank and it's going to get a new cannon that's going to be put on it, the process of developing that subsystem for the tank is going to go through the same life cycle that we're looking at here, and it's going to have the same type of LORA decisions placed upon it as that subsystem marches through its life cycle as well. Of course, it becomes integrated when it becomes integrated across the fleet, and then it just becomes part of the system, And then the LORA is now performed not just on a subcomponent or a subsystem now, but on the entire system. But up until that point, it is running its own LORA. So how do we deal with this using Opus Suite? Well, we're going to talk about mainly two of them here this morning. That's going to be Opus 10 and Symlox. Catlock, we're not really going to touch on too much, although it does have its place, and I'll tell you about that, but we're not going to showcase it. So Opus 10, if you're unfamiliar, is the steady state optimization tool that gives us our spares. It actually can perform the LORA itself. That's important, of course, but we also need to look at things from all perspectives as well. So again, we're optimizing performance, and availability is a great thing, right? We want high availability, but availability is not the end state. Availability is meant to be an insight into how many missions that system can perform, right? The A sub O. And that is more resident on the missions themselves. So having a high availability is good, but if that means that the system, let's say we have an unreliable system, it doesn't have a very large MTBF as a system, let's say 12 hours or something like that. Well, if your mission lasts more than 12 hours, the average system will not be able to complete that mission. And let's say it takes very little time to repair, right? It's replace a circuit card or something like that, like a radar. Well, if it can't operate, that amount of time and it breaks down, but it only takes a few seconds to repair and then the mission's over, you might have high availability, but low mission success or mission availability, that true A sub O. And so taking any logistic support solution, including a LORA, since the purpose of a LORA is to better the fleet, we have to look at it with respect to operations as well. We can't just say, well, this is the most economic way to go, or what have you. So let's look now at the application of a LORA. Like we said before, there are really two different main applications of LORA, and that's in planning, and I'm going to call it right sizing, addressing something. So in planning, that's going to be all the way up through, say, milestone C, and then right sizing is going to be from, let's say, LRIP through disposal, through sundown. When we say right sizing, we're usually addressing something. Again, A sub O, it might be cost. Again, cost can be a constraint in the DoD. We might look at downtime drivers. Again, this is to address A sub O. There might be some historical problems. We're going to get into a little bit more of that. But whenever we do that, there's going to be a certain scope of the LORA. That scope is, when I say scope, I mean what particular items within the LORA are we considering to actually change. Normally, when you are in early days and the system's young, you're looking to do a LORA on everything that you know can possibly be reparable, right? Sometimes we just know things aren't reparable. Nuts, bolts, washers, screws, we don't repair these, right? Sometimes we may be surprised at what can be repaired. Like, for instance, a tire. You'd say, well, tire is always consumable. That's not always true. Big tractor tires are consumable. They actually take the tractor tire off, they strip it down, they put in a big press with new rubber, and they form a new tire and put it right back on. So some things, especially as we move into the future with items like additive manufacturing and so on and so forth, what we once absolutely considered to be irreparable or consumable may not necessarily be. So we have to make sure the scope of our LORA is appropriate. Another interesting item about a LORA is that it has a lot to do with perspective. I know this really sounds strange, but let's go through a standard consumable type of setup. Let's say we have a maintenance policy for an item in a JLTV that's consumable. It's a PAOZZ SMR code. So what do we do? Well, we go in, and when that thing breaks, we pull it out, we throw it in the garbage, we go get another one for supply, and we put it in. It's consumable. Now let's say in that same JLTV, we have the transmission. Okay, it has an SMR code of reparable at the depot. Okay, so that means the organizational unit pulls it out, gets shipped to the depot, and then they quote unquote repair it. Now let's change our perspective to the depot. What are they doing to that transmission? Well, they get a transmission, they open it up, they're going to take out the plates, they're going to inspect the plates. Any plates that are worn down, they're going to throw away, they're going to put new ones in. They're going to look at the valve bodies, they're going to take out the valve bodies, they're going to look for broken seals and replace the seals. The depot is doing the exact same thing that the organizational unit is doing, it's just doing on a subsystem. Right? Unless they're bending metal or resoldering, and there are true repairs out there, don't get me wrong, but they are doing the same thing that the organizational unit is doing, just on a subsystem. So where that LORA is performed is important, because if we're looking at performing a LORA on the transmission with respect to the depot may want to know, is it better just to throw away the entire clutch pack or to replace the individual plates? Should the whole valve body go, or should I spend the time to take it apart and look for those blown seals? Right? So the perspective of LORA is also very important. We can't just consider, well, obviously the SMR code is written for the entire fleet, but let's also talk about that just a little bit here as well. So again, the LORA may be limited to a certain number of parts in service. Early on, it's probably going to be most of the parts, all the parts. But as time goes on, typically the scope of the LORA, meaning the parts that you're looking at changing that maintenance policy, tends to go down. And it's usually as needed, right? So ECPs, obsolescence, safety, downtime drivers, so on and so forth. These are typically triggers that get us to do another LORA, to look at something. Often, maybe too often, it is done on a single part. Hey, this went down, this is the problem, this is the alligator closest to the boat, we need to look at that again. Maybe a better policy would be to look at subsystems, maybe one subsystem a year, do a LORA. But when we do a LORA on anything, we have to include the whole system, because we are trying to improve the system, the fleet, the enterprise, not just the engine, not just this. You may think, well, Jerry, if I make the engine better, that makes the system better, right? Depends on what you mean. Does it make the system better? How? Does it make it cheaper? Certainly with the local LORA, you can do that. If you're looking at an engine repair or discard, or portion of it repair or discard, there is certainly a place there for certain that we could say, well, this is more economical, this is cheaper. So you can make the engine repair or the engine rectification process cheaper, but does that necessarily lead to more availability? Does that necessarily lead to a larger or a better fleet outcome? Even economically, does it? Not looking at the whole system at a time can lead us to actually creating problems, unintended problems, when we make a new LORA decision. And so there are quite a bit of pitfalls out there. Now, if I can, there are a few tools that I'm aware of that are out there on the market. Probably the most popular ones out there are going to be Compass and EDCAS. And so if I might, I'm going to compare some of these considerations against those two, because again, in order to get a high fidelity analysis done on something, you have to be able to consider as much of reality as you possibly could squeeze into the computer, so that it uses all those different data points to yield an answer that actually is applicable to reality. Right? I kind of mentioned that SMR code before. Sure, if you are at the very beginning and you just do an SMR code and say, it's POZZ, it's throwaway, or let's say it's repair at the depot. Okay, so that's blanket across the board. That is the SMR code, true. But there can always be and should always be other considerations to that as well, right? What if we have a deployed unit? That deployed unit is out in the middle of nowhere, is very far away from the depot, yet it's forced to ship everything back to the depot. Yes, it still has that SMR code, but that should be part of the consideration. What if because the availability, let's say there's a lot of units out there. It's Stuttgart or something like that, has a lot of different systems out there, enough to weight it so that the LORA might tip, right? We have to consider all these different pieces. So the whole system has to be considered, not just piece by piece. Now, in the case of, let's say, EDCAS, and Compass as well, so to my best understanding, I shall say that it looks at every single portion of a LORA separately, meaning each individual part. Now, parts have effects on one another as well, but even if you don't consider that, we need to consider the combinations that are possible out there, right? Let's just take 3 parts, for example. So we have 3 parts. Reparable, consumable are the binary choices that we can have. So we could have part 1 is consumable, then reparable, reparable. We could have reparable, consumable, reparable, all consumables. So there's 9 combinations to do, right? Now let's say for a moment that we are considering a LORA and we have a some kind of sunk cost that we have to consider. Let's say it's $45,000 for, we're doing a LORA on a starter, a generator, and an alternator. Okay, 3 items that are all standard motors, copper wound motors, so they need the same test bench and equipment to be able to repair. And there's a $45,000 setup cost. So how do you split the $45,000? If you're considering 3 parts, you say, well, I'm going to split those up so all 3 of those are $15,000 each. But if the system only considers 1 part at a time, that means you're assuming already that all 3 of them are reparable. That's not the same as saying, well, I'm not sure if all 3 are reparable. If one is only reparable, then it would bear that entire $45,000 cost. It wouldn't be split up. And so if you have a system like EDCAS or Compass that only looks at a single part at a time as it goes through its LORA decision, you can run into some problems, right? There could be some, are all those combinations explored at the same time? Well, if they're not, you have to make some decisions. So in order to get around this with, like, say, Compass or EDCAS, you would have to do all the combinatorics for that manually, right? You would have to have those 9 combinations for the different reparable, consumable. You might have to have a level, like location, where they're at. We're going to talk about that in detail as well. And then you're going to have to say, okay, for this one, this is, 22.5 thousand to these 2, or this is 15 to this one. And you have to get all that right, because each individual input you're going to have to do manually. You're going to have to do that manually in order to get the full breadth of then you have to get all the outputs and compare them. So not having a tool that's able to consider the entire thing at once and do all those combinatorics for you means you're only looking at a very small portion of the possibilities of a LORA. The whole thing about a LORA is to look at all the possibilities, right? Is that maintenance policy properly described? What if we have different units with different locations, different logistics delay times, right? Different shipping times. We have different number of systems. We have 20 here and 50 there. I mean, there's a lot of units out there. Take the JLTV, right? Infantry unit has them, comm units have them, anti-air defense, units have them, so on and so forth. All these different types, you have differing number of JLTVs. They operate at a different amounts, right? Some are always on the go, some doing convoys, some are just kind of sitting there and they pull the radar into place and they shut down, so on and so forth. Right? There could be differing variants. And what about all those common parts versus non-common parts? Can you look at all that in a single go? That's the complexity of a LORA that we need to come to terms with in order to get a good answer. Not only that, but we think about how a LORA is actually conducted. There are a lot of nuances in as well. Again, both cost and performance has to be considered, but sparing is also very much a part of that. You can't really separate sparing from a LORA anyhow, because if you're looking to better the entire system, having a repair versus consumable is going to affect sparing, and sparing affects cost, which can be constraint for performance. or the sparing can directly affect the performance. So you can't really disassociate the two. You can't disassociate a LORA from the sparing either. And when it comes down to the actual decision of a LORA, there could be lots of different examples of exactly how things get done. Do we consider just the children? Do we put children and the parent together? And I could definitely talk about that at the end of our presentation here. But when it comes to sparing, let's look at an example here. This is meant to be a very simple example. It doesn't have any of the nuances that actually occur in a real system, meaning that we're having a failure, which is down here on the bottom, once per week. We all know they don't happen like that, but for the sake of a simplest model here, let's look at some of these considerations. So we have this part. It has a repair turnaround time, an RCT here of 14 days. We're getting a failure per week. So for a single system, we only need 2 parts, a stock of 2, right? Because when this fails, by the time that third failure happens, it's repaired, it's back on the shelf, and it can be reinserted here. So we have all these down here. The light ones are supposed to say this is the same individual part as this first LRU. So the stock here is only 2. That's all we need for this. And that needs to be part of the LORA consideration by something like this, right? Where we have a part that is very long to be repaired. And so if we have a high failure rate, well, we're going to need a lot of stock for that. And if it's that amount, well, maybe the transit time and maybe the repair cost and the effort and the line space at the depot and all these sort of things might make that an invalid choice for a repair. Not to mention, can a unit actually stock that many forward? Maybe they're on ship, maybe they're deployed autonomously, maybe they're on an endurance mission, what have you. Is this just going to be a throwaway item now, or are they going to need to repair it? All right, then. So we're going to get into some examples now. What I'm going to be doing is I'm going to be hopping back and forth between some scenarios and Opus Suite itself. We've looked at what a LORA is so far. Right? I think we've talked about it in quite a bit of detail. And we've talked about some of those pitfalls. So I want to bring up some scenarios, some very legitimate use cases, I think, that almost any system would see. And I want to showcase, here's how Opus Suite deals with that particular LORA, but also I want to showcase what happens if we don't have that full fidelity answer and we make a LORA decision kind of on the other side. Some of this is going to be pretty intuitive, but some of it takes a little bit to get to. It's a little bit more hidden. The answer is a little bit more hidden, but once you understand it, it does make sense. And those are the things we want to avoid, right? We want to avoid those unseen landmines, right? The things that we don't know, the boogeyman underneath the bed. That's what we want to avoid, because the things that we do know about are far easier to avoid than those that we don't. So what we're going to have, if this is going to be a standard scenario that we're going to be using throughout all these examples. We have a not very complex, but certainly a, shall we say, normal setup here. And that setup is we have down here, we have units 1, 2, 3, and a deployed unit, call it unit 4. And those all have O-level capability as a baseline. Unit 1 and 2 have a I-level, an intermediate maintenance activity that is very close to them. Unit 3 also has one, but not as close. These are both supplied with parts from a central warehouse, and then that goes through the depot, or shall we say DLA for consumables, but all the repair parts go up here to the depot that the I-level can't service. But the deployed unit is very different. It has an overseas warehouse and has no, to start with at least, no repair capability locally. So we're going to be, and each one of these, by the way, these units have differing number of systems. As far as I know, this scenario that I just outlined here, which is not very, outside the bounds of reality. I'm not aware of any other system besides Opus that can actually take all that information in just to build that kind of station structure to be able to perform the LORA in the first place. All right, let's talk about the first scenario. The first scenario is going to be looking at the engine block, whether we're going to repair it or we're going to replace it. This could be anything. This is simply an example, and the model that I'm using here to showcase this morning is a notional model. It is using realistic type of values into it, but it doesn't exactly represent anything. Let's just say it's a general representation of a system with values that go into the model that are commensurate with what we typically see out there. So we have two options, right? Repair versus the reorder. All right, we have a common shipping cost, let's say common transit time. At least let's say it's common in as much as it's close enough. Of course, repair is a lower repair cost or a lower overall cost, but it takes a long time to do, right? Maybe that's a month, maybe that's 2 months, whatever it may be. On the other side, the reorder has a higher procurement cost, a lot more expensive to buy that block, but the procurement time, it comes in a lot quicker than the block can be repaired. So let's ask ourselves a few questions here before we get into the actual example. How much will this affect the system? Or how will this affect the system? In what ways does it affect the enterprise, your system here? By how much does it do so? And is a LORA decision universally applicable at every single point? Every single point of cost and every single point of availability. And if you have that, is it therefore then viable? If you were to ask an SME, I'm going to stock, 50 blocks at a unit, can you do that? They may say, no, you can't do that. We don't have the space. So those are the questions we're going to kind of ask getting into this. This is the setup. And now what I'm going to do is I'm going to switch over to Opus Suite itself. Just give me a moment while I go from here. Okay, just a real quick check, Matt. Am I showing Opus now?
We got you. You're all set, sir.
Awesome, great. Let me take everybody through just a really quick run of what we're looking at here, because there's a lot. So first we have our truck. So this is the system in question here in the center, right? It's pretty simplistic. It has a few subsystems, a chassis, a cab, an axle, so on and so forth, and it has parts associated to that. It has some indenturing here as well as some subcomponents. We'll be focusing here on the engine specifically, and then again in this particular item specifically the block. Now here we have our station structure. This is exactly what we said before. I'm simplifying it just a little bit here because if we're looking at something like SMR code and we have units that are deployed, sometimes you consider that within your SMR code LORA or not. But just for the sake of argument, we're just going to say we're just doing the state side stuff because that's what the SMR code is going to be based on. Now, when we calculate this, what we get is called the cost over effectiveness curve. On the X, we have the cost. This is the life support cost for the scenario length, which I believe is 10 years here. And then on the Y, we have, in this case, availability. We can show other things than availability, but for now, we're just going to be looking at availability. And believe it or not, it actually performed a LORA there because this is a pretty simplistic system, doesn't have a lot of parts, and we're only looking at the block, so it was able to do the LORA relatively quickly. In fact, that was the LORA calculation, and it did consider the entire system at a time because not only do we have a LORA, and I'll show you that here in a moment, but each one of these pieces as well also has a bunch of different metrics we can look at. And these are all we can look at. We can look at the consumption rate, let's say the repair rate, because we know repair actions per year. We can look at cost. We can look at demand rate, all kinds of different things you see I could pull up here and look at. But we're really here for a LORA, not the sparing per se, although that's going to come into it. So I'll go ahead and select all the points and I'll run a report. And the report would come here, and I've already pre-done it, so just the LORA is available. And here's what we have. So for those of you that are uninitiated, this can look like a bit of an eyesore, but what we're saying here is these point identifiers correspond to the points here that are climbing up the availability curve for more cost. This is the part in question. We were doing it on the block, and this is the station identifier. So right now it's saying all the way up to point 14, we are repairing the block. There's that block repair action. This has to do with the specific task that rectifies that piece, in this case, the block. It is saying that we repair it all the way up to point 14, but then from point 15 on, every single unit, or at least 3, is going to now reorder it. Well, why is that? Why would you start to reorder if it's so much cheaper? Well, the reason is, in this case, because in order to realize higher levels of availability, you can no longer repair it. It's just not fast enough and it's not viable. Let me show you what I mean by that. So I told you that the switch happened between point 14 and point 15. Now this is going to get a little bit deep here, if you will, but I'll go ahead and I'll just pull those 2 points up. Let me reduce this. Well, let's start with just the stock size here. We'll start with just the stock size. So what is our nominal stock for that particular part between 14 and 15? Number 14 is a repair, and 15 is a reorder. You may be very surprised to find out when I look at the block, look at the stock size. So for a repair, we have to stock items. You say, Jerry, why is that? Well, the answer to that is if you want to actually reach this 86% availability, because of the length of the repair, it's not good enough, right? If you were just to have no parts, no extra blocks, you just have whatever you have, and when it breaks, it goes to the depot, it gets repaired, comes back, gets reinstalled. The length of time that it is not available, not in the system to actually be on the truck, you're not able to reach that level of availability. And so you have to, in this case, you're going to actually have to stock 28 of these at the wholesale. Interestingly, now look at this, however, but you don't stock any over here at the first point of reorder. Well, how could you possibly, if you're reordering it, how come you don't have a stock? The reason is, in order to hit this 88.92% availability, this also means that we're willing to accept about 11% non-availability. Those parts, the block comes in so fast or fast enough that the transit time that each one takes to get to the failure only accounts for a much smaller percentage of time. So you don't even need to stock them. So in order to conduct the repair, we are going to need to stock 28 blocks, but if we do a reorder, you actually don't need to have any on hand at all. As soon as it breaks, you just order it, and it takes 2 or 3 days to get to you, and boom, there you go. Maybe in the same way, if you have a busted tire, I suppose, on your car, and you call up the tire shop and you say, hey, I have a busted tire, I need to bring it down to get repaired. Well, it's Friday, we have a whole bunch of stock, can't get to you until Tuesday, but you need to get in line, so go ahead and come on down, drop it off on Friday, we'll have it there for you on Tuesday. Or you could just go down to your O'Reilly's and buy a new tire and have it back to your house in 30 minutes and just do the replacement yourself. That's the type of difference we're talking about here. So the devil could really be in the details on this. It doesn't seem intuitive, but this is really what's happening. Now, we were talking about the outcome of a pitfall like that. So here is the curve, like I said, where we are making a decision whether to repair or not. What if I say, well, I want to I just want to do a repair because that's what we do. I want to repair, and we have that deployed unit here, the one that's out there some of the time, right? There's unit 4 out here that's out there some of the time. So what we're going to do is say, all right, we're going to institute that repair, not the reorder, but the repair capability, and let's see what happens. So I'm going to run this as well. And we get these two lines that are very far separated from it. This is the original line that we looked at just here before. And it gets up pretty high, right? It gets up to about 97% availability. This one, this is the repair only. Well, it gets to 93, which is not bad. That's not bad, but it doesn't reach the same level it was before. The big difference is, look how much more expensive it is. If I take this 81% point and I find something that's close to 81% over here, there we go. You can see the delta in cost is $63 million in this case over the course of 10 years. Terry, how can that be? Well, the reason is because if we go to that stock size, right? In that new scenario, if we're repairing it, we have to stock 72 of those things at this wholesale and 21 at this wholesale. Remember, I said it. Sometimes if something's repaired slowly, you're still going to need a lot of stock to be able to make up for that time that it's in repair. And so in this case, to reach those higher levels of availability with a repair maintenance policy, you're going to be spending oodles of more money. So this is a really good example of how something that is cheaper can really actually be a lot more expensive. That's why we just don't look at the single part, right? We just don't look at the block. We have to look at the entire system, because if we don't, we're missing the forest for the trees. All right, let's share my screen again over here. Let's get to that second scenario. All right, scenario 2. Excellent. So scenario 2 is going to be something very, very common. I alluded to it before. This is going to be when we're looking at resources. We're instituting we're looking at instituting some kind of new maintenance policy. We have these different options, but there is a sunk cost associated to it. In this case, we're going to look at the starter, the water pump, and the ignition system, or some part of the engine. So again, we kind of have the same thing. It's going to be a low repair cost, about same shipping time, same transit time, a longer repair time, but we also have the setup costs, right? And then in the reorder side, we have a procurement cost that's high, but a short procurement time. So again, really importantly, are all things being considered at the same time? How do we split up and account for that setup cost? Right? Do you have to do all those pre-calculations in your modeling, like I said before, like you would have to do with something like Compass or EdCast, right? Would you have to go in there and do the combinatorics yourself, look at all these and run all of them, compare all, however many is 27 different answers to look for the best LORA decision? And then, of course, we're asking all those same questions that we were before up here. How much does it affect the system? Where does it affect the system? Is it universally applicable? Like we saw before, a repair was applicable only up to a certain level of availability, and then is switched. And then again, is it viable? Can we stock 72 engine blocks at a local I level? Probably not. All right, so that's scenario number 2. Let's go back over to Opus Suite. There we go. I'll go ahead and close this one out.
We can see your screen, Jerry.
Excellent. Okay, here we go. Here's our scenario 2. And this is, as you can see, it's the same scenario, exact same thing. The only difference is now we're bringing in a technician. We have 3 parts that we're looking at in this particular case. And I'll show you, at least in this case, the table. And this presentation this morning is not meant to make anybody an expert how to use Opus. It's simply here about the capabilities of Opus 10 when it's performing a LORA. So if you want to know about, if you're a current user and you want to know more about this, it's actually contained in our Opus 10 Advanced course. But specifically, we're looking at this starter, the water pump, the fuel pump, and the generator. those are the 4 parts that we're going to be looking at here this morning. They have a $45,000 setup cost that for a technician that can repair any one of those 4. So to set up the technician, 45 grand, and it can repair any of those 4. So Opus needs to consider all the different possibilities at the same time to come up with what is the best. And as we run it, we get the same thing. It did just perform a LORA right then. Yes, it's a simplistic system. More complex LORAs will take a little bit more time. This one happens to be pretty quick. We're going to look at all these points just like we did before. I'll go ahead and run the report. We'll take a look at that report and we'll see here that, well, we have all these different points, right? Here's the point along the curve. So point 1, point 1, point 1, point 1. When we're looking at this, there's 4 of those because every single point is considering each one of those, the fuel pump, the generator, the starter, and the water pump. All right. Well, we're repairing them all right now. It's all being handled through this engine repair task. As we advance through the points, getting more availability, we see right here around point 20, we start hitting a reorder. But it's only on the water pump. And in fact, if I go ahead and just fast forward through this, you can see eventually we're doing the starter and the water pump, but not until really high levels of availability. And so in this particular case, that 45 grand was really only good to use or to make the water pump in this case to be a reorder for whatever that reason was. Maybe it was really fast to come in and maybe the cost wasn't so high. And so that was the most applicable or economical and best for the system. Again, we're still talking about availability here. Still talking about availability at that point. And not all of them ever became reorders. Only half of them did. Now, so we're talking about those parts. There are 4 parts, with the resource associated to it. That's something like 64 different combinations that we have to do just on those 4 parts. And then you have to reference that to the overall system availability. And oh, by the way, we still have stock size we have to deal with here. How do I support that maintenance policy at that point with whether this is initial stock or this is your TSL, your target stocking level at your warehousing? Either one, that has to be right sized in order to fit the LORA decision as well. All done for you here very, very quickly. So there's a good example of when you're using resources, it's not that straightforward. Instead of doing it 64 times to come up with just on 4 parts, we can do it all very, very quickly. All right, let's do the last scenario here.
We're back on the slides, Jerry.
Excellent. So here what we have is we're going to have something, what we call location of repair. Now, a LORA typically means level of repair, but we're assuming that all eye levels are the same. We're assuming all depots are the same. As Matt said, I spent some time in the Marine Corps, and I could tell you that the 2 depots the Marine Corps has, Barstow and Albany, they don't have the same capabilities. And so Barstow can't repair as much as Albany. And so if you have a lot of things that are stationed in, say, Camp Pendleton in California, in order for them to repair it, they have to go cross country. Well, the transit time is much different. If you were to say all depots are all depots, right? This is the way that Compass describes it. You go into Compass, there are X amount of units. They all have the same amount of equipment. They all have the same transit time and the same capability. But if that's not the case, if you were to do that, it would say, well, just ship everything to Barstow, and it could be a repair. But it could be that because of the transit time it takes to get from Camp Pendleton over to Albany, Georgia, that may be the trigger at 80% availability that switches it over to no, we need to start thinking about reordering this at this point in time. So the level of repair analysis in this particular case, we have the deployed unit over there, and we're going to be looking at the same thing, I believe, as the block. And even though the SMR code is going to be universal across the board, we're going to look at, because we need to know, does this unit need a letter to the commander authorizing them to be able to conduct limited eye level repairs on just a particular amount of, or particular type of part, right? In this case, the block, so that it doesn't have to ship everything back all the way back to CONUS to the depot. Now we'll say that the repair cost and time is the same. When it gets there, when it gets to whether it's at the deployed unit or if it's at the depot, the repair cost and time is going to be the same. If it goes back to the depot, you have a very high shipping cost, and you have very long transit time. If you do it locally, minimum transit time, right? Basically none. No shipping cost. It's not going anywhere, but you have to have two other things to be able to support that. And then you have the setup cost. Some sort of technician, tools, and equipment need to go out there in order to bring the capability that repair demands. Secondly, you're going to need some sort of initial stock. Remember, just because something's reparable doesn't mean there is no stock. So we need to figure all that stuff out. So is this going to fix a problem? Does it fix it at all levels of availability or just at some levels of availability? And what about mission performance, right? We're going to get back to that here in a second. So let me go ahead and stop there again. Come over here. Go back one more time into Opus 10, or before. Go and close this out. And we will bring up a very familiar site. Here we go. Here it is again, the same item. And we got this unit out here again. And instead of saying if something is discardable or reparable, we're going to turn on its head and talk about the task. Where can the task be done? We're going to give the option to Opus 10 to say, what if the task could be done down here at this unit 4, right? It's deployed, longer shipping time. It has less systems, only 20 systems compared to the other units, which have more. But they probably run them a lot hotter as well. So let's go ahead and calculate that. This is still a LORA, and we get the curve that we're all familiar with now, hopefully. And we're going to, again, select them all. We're going to go in here, and we're going to run a report. We'll check that report. And you can see that we're doing a block repair, which is done at the depot. This particular task is done at the depot, but I can maybe expand that. Well, I think we could see it, but I'll expand it just a little bit. We could see at about 0.12. Now Opus saying for unit 4 and only unit 4, not 1, 2, or 3, but just unit 4, it needs to start doing that repair here at 0.12. I'll go back here. See if we can find 0.12. There's 15. There's 12, 79%. So if you say, well, Jerry, what if I don't need 79% availability? What if I just need 70% availability? Then I don't have to repair, right? Or I don't have to reorder, pardon. Possibly. Depends on the units themselves and how they're being utilized. This is where SimLocks comes into play. So for the sake of time, I'm only doing SimLocks on this one example, but it could be done on all the examples that we covered already. And let's kind of show you what that looks like. So I'm going to get out of here and I'm going to go into SimLocks. And here we have that system that we picked a 70% point for. All right, we have 70% point. It's great. It's riding right about 70%. And you say, well, that's all the availability I need. That's great. This is the enterprise level. And Opus 10 gives you an average availability over time. Average availability of 70%. That might be, you can actually look at it over time and see what it's doing. And it's riding pretty even. It has some high points and some low points when operations maybe aren't happening. But yeah, it's riding about 70% the whole time. Well, it looks good, right? Well, maybe. Let's look at what the units are doing. So now when I break this down, it's a different story. We have those 2 units that are directly supported at 75%. Unit 2 that is distant from it is a little bit lower, but look at that deployed units at 46%. Even though the average is 70%. So now what I'm going to do is I'm going to go ahead and institute a a local repair. We're going to see what this does for the missions, or the availability in this case. So it's going to go ahead and iterate it. It's going to take just a moment here, but what we're looking at is we're looking at if I were to put that local I level for the block down at Unit 4. In OLing Unit 4, what's going to happen to the entire system, not just at Unit 4, the entire enterprise? You might be surprised to see that we get a much better availability across the board for everything. Now, why is that? Why are we getting 16% more availability? Well, if that unit that's out there, those 20 that are out there are being ran hard, put away wet, and they're taking a lot of failures, and those failures are all going back to the depot and they're gumming up the depot. If we start repairing at that deployed unit, well, that's less stress on the depot, and therefore the depot can turn around items faster, right? And get them back to those stateside units, so everybody's benefiting. And in fact, in this case, if I go ahead and go here, you can see now we've brought that Unit 4 all the way up to be even with everybody else, and they're all experiencing much better availability. This is the importance of looking at the entire enterprise at once. And you might say in this 70% case, well, that's what we're looking at, right? We just need 70% availability, but I can guarantee you any portion of the DoD will say 70%, but if you told them it's 46% at the deployed unit where the tip of the spear where you need to have it, there's not a single portion of the DoD would say that's okay. So we have to look at things in depth. They're not always really intuitive. They're not always, yeah, I can understand that immediately. Sometimes the devil is in the details, and sometimes those hidden things, like we saw, like a whole bunch of stock for reordering or repairing rather, and none for reordering. It doesn't make any sense. But when you think about it a little bit and you see how it interacts, actually it does. That's more of the just-in-time logistics type of model, if you will. Oops.
And we're back to
and so, yes, great. And so for that LORA and for Opus Suite, there are lots of us out there that are already using it. Almost every single service that uses, especially the Navy that uses the Opus capability, is using it for LORA. In fact, I think it's mandated in the Navy for use of LORA. Lots of our customers out there within the defense industry are also using LORA for this specific reason as well, to get that highest fidelity answer. Now, it's not always easy if you're using something else to switch over to a new product. How do you, especially if you're in industry, right? How do you tell whoever that, well, we switched over to a new product because it gives us better answers? Does that mean that the other LORAs weren't full? Again, it depends on where you are in that life cycle, right? It really does. The more considerations, the more complex your system, the more asymmetric your support organization is, the more that you're going to need to consider all those differing inputs to a LORA so that we can actually reach the right answer. And at that, I think I've covered all the material that I'd like to. So, Mr. Moderator, we'll turn it over to questions and discussions.